Yeah, and this is a third session of your FTP. Okay. So in this third session, I was asked to touch about the quantum mechanics or quantum physics required for quantum computing. Uh, so I immediately asked your organizers to share me what was things covered in yesterday's session. So I just gone through the yesterday session. I was just checking little bit now also. Okay. So here I see. Okay. So quantum entanglement is also touched. Okay. So yeah. Right. Yeah. Right. So yes. Looks like some introduction to quantum physics and introduction to quantum computing is also touched. So what I'll do, some mathematics here and there which is missing, okay? That mathematics I will try to cover, okay? Right? So if you happen to have any questions, you please, I think I can see the chat messages. Let me see chat messages. Okay, so you can just put the chat messages and I will just check and try to answer the questions. Okay. So we have, let's say now 1.5 hours. So within 1.5 hours, we'll try to cover as much as possible the quantum physics, uh, how it led to quantum mechanics. Okay. So that's what I was asked to cover. Let me see. Yeah, I was asked to cover quantum mechanics for quantum computing. So some basic quantum physics was introduced in the first session. Introduction to quantum computing was given in the second session. I will try to connect both of them, okay? And I will show you where are we at with regards to quantum computing right now, okay? Okay, so fine. So the title says Quantum Computing Fundamentals and Applications and Research Opportunities. Okay. So quantum computing fundamentals means I have a quantum physics. Using quantum physics, I do quantum computing. That is what I meant, quantum computing fundamentals. Then having some knowledge on quantum fundamentals and computing fundamentals, we can do to pursue some applications and see what are the research opportunities which we have. Okay, right? So let me start the first slide. Okay, so the first slide is this person. I think yesterday while introducing quantum computing, the resource person might have showed this person's photo. So in a way, he is father of quantum computing because he is the one who sparked the idea of quantum computing. Okay, right? So how did he spark the idea is basically back then people were trying to understand how the chemical processes or biological processes takes place in the real world. Okay. For example, if you just take a photosynthesis, so photosynthesis is a conversion of solar energy into required nourishment for the plants. Okay. So it is happening with a perfect manner, with a very good efficiency, but we humans were unable to do that with the same efficiency or very good efficiencies. So that is because plants are actually going through some kind of a path, traveling path, which leading them to perfect efficiencies for them. Okay. So probably there are multiple parts. Let me use my hand notes. Okay. So for example, if you just take a photosynthesis, okay, right? So in the photosynthesis, plants are there, okay, leaves are there, okay, that take a sunlight, right? Convert that to from the minerals it takes with the 80 to 100% efficiency, it convert okay, convert solar energy into the energy of the plant, energy for the plants, plant growth. Okay. So why it is possible? Because let's say there is a path from 0 efficiency to 100 efficiency. Let's say there is a path. Okay. So, and there is a path to 80% efficiency. There is a path to 60% efficiency. There is a path to 40% efficiency. Okay. So there are all the paths are there. The plants should reach to exactly the 100% efficiency by choosing that particular path. Okay. But just like we take it in a real world scenario, if there are multiple paths are there, and if I have to go to a particular location, let's say from Bangalore, okay, from Bangalore to let's say Cochin, okay. So there are multiple paths of different time taking, different energy taking, different like many factors are there. So I want to have optimal travel, less resources I want to consume, and I have to be more quick. So that is the one which is the best is 100% efficiency one. Okay. So there are so many paths. Unless I don't know which path takes what time, how much resource it takes, I can't pick that. Okay. What I should do, I should go through path one and find out how much, go through path two, go through path three, and go through path four. And then I will say path four is the best, and I will tell to somebody else, you to choose the path four. If not, if I don't want to consume this much of energy, let's say I will ask somebody what is the resource required to go through path one, path two, path three, path four. And then at a time, I will see all of them together on a paper and I'll pick the path four. Okay. So here the number of paths are very limited. For fine, I can do the processing or analyzing. But the thing is, if there are billions of paths are there, okay, billions paths are there. In that case, finding the right path, finding the right path is very difficult. Okay, because I have to see them all difficult. Okay, so plants are somehow using some kind of a quantum in nature, try to see all the paths in one go. They put all the paths in kind of a superposition and pick the right path in and chooses that right path to convert the light into the right efficiency. Okay, right efficiency. Okay, so back then, like in before 1960s, people were trying to analyze how the photosynthesis is so effective, and a lot of factors are involved in taking that right path. So all those factors and parameters, they were trying to use a classical computer to assess the analyze, but people are failing. A lot of parameters are, a lot of data is required, a lot of processing is required. So people were failing. So that is when this person said, you better design a classical quantum computer which could take the quantum nature into the consideration and do the analysis and can predict how this chemical processes takes place in quantum systems like trees inside at a quantum level. Okay, so that is how he sparked the idea, and that idea was picked up by David Deutsch, and he came up with a universal quantum computer purely based on two states, just like a two quantum a coin being head and tail. So from there, he just designed a theoretical model where we can do small calculations. Okay, right? So universal quantum computer was invented or theoretized or model generated. Then in 1992, David Deutsch and Richard Joyce are together gave the first quantum algorithm where one can do some kind of a mathematics or some kind of a computing. Okay, that is good. So the theoretical formation of quantum computer was given by Deutsch, and then Joyce joined with him and came up with an algorithm, quantum algorithm. Okay, that's good. Next, next, there's another person called Benston, Ethan Benston and Umesh Vajrani. They two together, they gave up some computing task where classical computers are significantly so in executing the task, but quantum computers, whatever Deutsch came up with, was very good in doing that calculation. Okay, and even if you allow a small probability error, that also is not a big issue here. Okay. So later on, another scientist by name Daniel Simon showed that there is an exponential speed up is possible in finding the period of some function. Okay, if you use a quantum computer, you can find the period of a function when much faster than classical computer. So this has all happened within let's say some 20 years time. Okay, so from 1985 to 1993, so about 8 years there. And then from 8 years onwards, okay, in 1994, the Peter Shor came and he gave a very powerful algorithm called Shor's algorithm. Okay, so what Shor's algorithm does is, okay, right? And if you see existing communication, okay, is being protected by RSA encryption. Okay, all our emails, you take emails or bank transactions, any secure transaction you take, okay, which is all based on RSA encryption. What is that RSA encryption is? So if you just take a small number like 49, you can find the factors 9, so 9 into 7 into, okay, 7 into 7. Okay, if I give 81, 9 into 9. Okay, if I give 49, 81 together, finding a factor is not manually possible quickly, but I can do it with using some computing task. Let's say I give one more large number, let's say 27,894,9,371. So finding what are the factors is slightly difficult. Okay. So what what Shor's thought is, 1 minute. Okay. What Shor thought is, we'll take large prime number, okay, such a way like a large prime number, not sure, even RSA encryption was based on that. Okay, let me give that RSA encryption. They will take a large prime number. Let's say if it is difficult, to find the factors of this n. So n r comma p is n. So finding r and p is difficult. Okay, difficult to know r and p. Okay, so how difficult is you given any computer, classical computer, existing computer is unable to solve, unable to find that r and p. Okay, so that is how the RSA encryption is solved. Question is, how do we get n and how do we get r get connected? So for that, what they did, they start with large prime r and p. Two large prime numbers they will start and they multiply and they will get n. Okay, this n can go in public. N could be used in public. Okay, but R P are like say, let's say banks. Banks keeps R and P with them, okay, and distribute or give away N to customer. Okay. Now customer can, like while putting password, he will put N value. The bank takes the N and it just try to match with R and P it has with them. And if R and P product matches with N, so then straight away banks connects your login credentials. So that is how any password will work. Public key cryptography, this is called. Okay. So now that is the Shor's algorithm. Now Peter Shor came, he said he used a quantum Fourier transform. Okay, let me elaborate. Quantum Fourier transform. And he said he can find the factors of the large prime if 10,000 qubits, perfect qubits are given to him. Okay. So if he has a 10,000 perfect qubit, he can crack the encryption. Okay, so that is good thing. So right now we are in 1,000 qubits. Okay, soon the perfect 10,000 qubits will be reached. So the RSA encryption is going to be obsolete there. Okay, so the next one is Grover's algorithm. So it is given in 1996. What Grover did is he used the idea of the vectors. Okay, simply rotation of a vectors he took, and he said if unstructured data is there, even if you unstructured data is there, okay, now Grover's algorithm, he is from India, Grover, okay, Love Grover his name is, he said it is possible to find anything or any item from unstructured data in quadratic speed. What I mean is if n is the data size, okay, if you want to find an item from n, you can find in data square root of n steps, you can find the required element. I'll say required. Okay, that is very commendable. The existing classical algorithm would require more than square root of n number of steps. Okay, so Grover in 1996 gave a very, very good, powerful algorithm. So people were started accepting what is quantum computing is capable of by these two algorithms. Shor's and Grover's algorithm was an immediate effect actually. Okay, fine. So let me go back. After that, the Seth Lloyd came and he gave in 1996 the some biological process, understanding biological process using universal quantum computing. So finally, he achieved what is the main agenda of quantum computing invention. Okay, and the idea which sparked by Richard Feynman. So he explained how biological process takes place, quantum mechanical process, and he used quantum simulations to show that, and which actually in fact led to few drug designs. Okay, so drug designs would require a lot of time, so which is can be accelerated by using this quantum simulations. Okay, right? So as you can see, the trends in quantum computing range is started in 1980, and then this was very slow in first 20 years. Later on, it became very, very steep. There is a very good research is happening from the past 20 years. Okay, right? Now, how classical memory is realized in classical computers? The basic physics, as you guys know, there are atoms, okay? There are electrons revolving around the atom. And let's see how classical memory is realized. Having understand the classical memory, what we can do, we can use that understanding of classical memory. We go on to understand the quantum memory, how it works. Okay, in that way, we can connect the classical physics and laws, what you understood in the first session, and the quantum computing introduction you was given in the second session. You connect both of them and understand how the quantum computing is taking place these days. Okay, so for that, let me use a quick notes, my notes. Okay, right? So this is electrostatics and electrodynamics. Let's say electrodynamics means electric fields are electric charges are moving. Okay, as you know, if there is a positive charge, it emits electric field lines. Okay, electric field lines, a positive charge Q. But if the charge is moving in a line, if the charge is moving in a line inside a wire, what happens? It creates a magnetic field around. Why? This is because the electric field actually varies. It is supposed to be a straight line here, but because of the movement, it becomes some kind of a curved around. It cannot be straight line. It can be so something which is traveling, it becomes some kind of a curving. Because of curving, Maxwell said if the electric field lines are changing in space, curving around, so that is expressed in a mathematical equation. Curl of E is equal to minus dou B by dou T. What it is saying, it is going to generate varying magnetic field. Okay, varying, the curling electric field is going to generate time varying magnetic field. If you solve this differential equation, what you get is Biot-Savart's law, which says there is a magnetic field line are created mu naught by 4 pi into I dot dl by r square. So what this magnetic field is, the solution of the Maxwell's equation. Maxwell equation. Okay. The solution is use of Biot-Savart's law. Biot-Savart's law. Okay. What it is saying is if there are charge moving in a certain location, small volume element, a line element dl, okay, okay, if the charges are moving, those charges are going to generate a magnetic field around that moving charge element because the electric field lines of that moving charges are actually curling around because in space, because of curling around, magnetic fields are generated. Okay. So now let's establish there is a current carrying wire is there. The current is there going upwards. So the magnetic field is there in the around that. Now what I will do, there is a current, there is a magnetic field. Okay, so around that. So what you do, you just curl the finger around, okay, or show the thumb towards the direction of the current, and the curling fingers will give you magnetic field. Okay, now what I will do, take the current carrying wire, instead of straight line, I'll just loop them around. So the current is going like this. Now, at every point, there is a magnetic field lines curling, right? Magnetic field lines. Okay. Interestingly, inside the magnetic field lines are all add up. Add up. Okay. Outside, all magnetic field lines get cancelled. Outside, magnetic field strength cancels. You can see the direction. Okay. So magnetic field due to this element is cancelled by this element because of this element magnetic field is inside, because of this element magnetic field is coming out. So in that way they both cancel. Okay. Because of this, outside magnetic field line strength cancel, but inside they add up. Magnetic field adds up. That is very, very interesting. Because of that, what happens? If there is a curling current carrying wire is there, it is going to generate a magnetic field. So that magnetic field is just like a magnetic dipole moment. So north and south pole, just like a bar magnet, where magnetic field coming out and enter, magnetic field coming out and enter. Okay. So this is a small bar magnet. A current carrying loop, okay, you can say DC, direct current carrying loop, is equivalent to small bar magnet. Okay, so inside the atom, if you just see, there is a nucleus. There are so many orbits are there. There the electrons are paired. That is not going to make any difference. Just to see the valency orbit where single electron is there. That is the one which is going to play a game. So it can stay in the outermost orbit or it can come to the innermost orbit. Okay. So now whenever electron is revolving around that orbit, it is just like a current carrying loop. So electron is revolving around, it is going to create a small bar magnet like north and south pole. It's very interesting, right? So what people did is they took a small magnetic strip. Inside the strip, they arranged all the bar magnets of the electron rotation in such a way, all pointing towards the left side. North, south, north, south, north, south, like that. Okay? So the moment if you do that, what happens? Okay? Right? What happens if you move that? All of them arranged, you can call them as zero. If you arrange them south, north, so you call them as one. This is how classical information is being stored. Okay? Right? So, okay? Okay? So there is a zero here. Again, I will arrange north, south, north, south, north, south, north, south. So this is zero. So in this way, I can store a binary string. Binary string is stored. Binary string is stored. And from there, memory is okay. So okay. So the memory is realized here by arranging the the small bar magnets, bar magnets of individual atoms. Okay, individual atoms. Okay, so this is how classical memory is realized. So that's very good. If you see how many number of atoms here, so the billions of atoms are involved, are needed, okay, needed for realizing one single bit. Okay, that is a take home here. Now, if you get back and see, okay, and you can record the data and you can retrieve the data by arranging the bar magnets. Okay. Now, when it comes to quantum regime, as it was told yesterday, let's say if there is a photon comes into the atom, the photon can be absorbed or not absorbed because it's a quantum in nature. At a quantum level, things are not certain. It is probabilistic in nature. Okay. So probabilistic in nature means if I supply a photon, if the electron is in the ground state of an orbit, it might attract or it may not attract. Okay, if I perform the experiment several hundred times, out of 100 times, sometimes it absorbs, sometimes it doesn't absorb. So we can say that it is existing in a superposition of absorption and not absorption. So to understand that, like people started using the wave nature, because if I create a wave by creating, like adding a disturbance, that wave happen to exist everywhere. It is not located in one location. So it shows its presence everywhere by distributing the disturbance in a form of ripples. Okay, right? So, which means which means I can say electron is so small, it is going to show a wave nature because the de Broglie wavelength, or like de Broglie gave a wavelength connection to the size of the particle and its velocity as lambda equal to h by mv. Okay, what I mean is if you just take de Broglie wavelength is equal to h by mv. H cut means 2h by 2 pi. Sorry. Okay. H by 2 pi. That is h cross. Okay. Now, what is this is? It is a chance whether we see a quantum wave nature in a particle or not. Or a particle shows a resemblance to the wave nature. It is not becoming a wave. It shows a resemblance to the wave nature. What I mean by that is, if I just take a one-dimensional box, if I just put an electron, 1D box, okay, electron is considered. If I just take an electron, it shows its presence in such a way, at some point the electron presence is there, at some point electron presence is not there, okay, and it oscillates like that. So at some point electron presence is there, at some point this is the location, no electron presence. Okay, and here also no electron presence, but there is a maximum presence of electron, some probability. So this kind of a probability distribution people saw, this is very similar to the wave nature, because if I create a wave, okay, which is something like this, okay, let me draw neatly. Okay, so let me draw a straight line. Okay, so the wave is looks like this. Yeah. Okay, so if this is a wave, psi of x, and if you just take absolute square of psi of x, okay, let me draw with a separate color. Okay, so absolute square of, okay, right? So this would be psi of x absolute square. Okay, so this is exactly same as what we saw here. Okay, so that means electron shows particle nature by virtue, and also it shows some kind of a wave nature. So wave nature is connected to the electron presence. So people thought, can we use that to realize a memory? Of course, yes. So how did they choose is, okay, they took two ways the electron can exist at 2 points in the form of wave, and they try to realize a quantum qubit out of it, a quantum memory where 2 bits information can be stored. Okay, this is our Schrodinger equation is is how did we get a wave function description, like a wave nature. This sinusoidal wave, what I have given here, is actually derived from solving the Schrodinger equation. Okay, right? The psi of x, let's say we don't know. Its system is existing in a potential well of u of x. Okay, there is an energy which system can exist with a E. And then knowing the potential u, you can just find out what is the solutions of psi of x. If you see, it is a sine function in 3 dimension. If you reduce to 1 dimension, you will just have one sinusoidal function just like here. I'm sorry. Okay, right? So, and also this sinusoidal function tells me, okay, the wave particle cannot be certainly located with a fixed manner. It goes here and there. Because of that, I always make a mistake in finding its position and its momentum, and their product of errors will always greater than Planck's constant. So that is a Heisenberg uncertainty principle for you. And people thought, can we use that idea to realize a quantum memory out of it? Okay. So what is that quantum memory is? They take a two-level atomic system and send a photon into the system. The photon sometimes absorbs, sometimes it doesn't absorb. Okay. So what I mean is a superposition state. 40% photon gets not absorbed, 60% absorbed, and the electron goes to a higher state. And in that case, I can try to put the mathematical form of that quantum state. Okay. So 40% not excited plus 60% excited, let's say that is a quantum state or a quantum wave function for me. But the overall probability is summing to 100%. But wave function for me means what? It's a sinusoidal function. But whatever I have written here at the top, it's just a probability sum. To make or to bring some sense into this, moreover, if I just take the psi of 40% plus 60% equation, if I just take a absolute square, I am not going to get the presence of the electron. Okay, the way we were getting wave function case, how did we get the presence of the electron maximum at some point, minimum at some point, right? That is not getting, we are not getting that here in this case. Okay, so for that, what de Broglie thought, okay, sorry, what Dirac thought is, can we introduce a new notation called Brand-Ket notation? Okay, so what I mean, let me use my hand notes there. Okay, so Dirac introduced a bracket notation. So he took the word bracket and the left hand side he added left angle and the right hand side he added a right angle. If you add a straight line to both of them, okay, if I just say add a variable, so this is called x ket. This is called x bra. Okay, and C, which is not used here, actually it is used as an operator. Okay, it's an operator. It can be some kind of a unitary operator or it can be a gate. Okay, it's kind of a probe. So that is how Dirac introduced. He introduced a Dirac notation so that quantum state is equal to alpha not excited, okay, plus beta excited. Okay. So it's just instead of writing not excited, excited, there are only two opposite cases. So I will say 0 is not excited, 1 is excited, 0 stands for ground state, 1 stands for excited. Okay, 1 ket state. Now, alpha and beta tells me alpha absolute square times the electron exists in the ground, beta absolute square times electron exists in the excited state. That is a superposition for you. Okay, it is just like you can just take electron to be existing on two orbits. Okay, what is that is there is a maximum probability here. Okay, and no probability at all in the middle, maximum probability here. So this is the probability distribution you can have on electron. So the probability distribution is maximum here and maximum here, exactly 0 at the center, 0 between two orbits. Okay. Okay. Right. So, right. So now I take a maximum chance of existing here, maximum chance of existing here. This is correspond to alpha square. This is correspond to beta square. And I'll realize a superposition state, a quantum qubit state like here. Okay. So that is how quantum memory is realized. Okay. So quantum memory is realized. Now they started calling it as a two-dimensional quantum vector. Okay. So why it is called a quantum vector? Now, if you just carefully see, this is resembling just like a two-dimensional vector, which is like R is equal to xi plus yj. Okay. So here the basis elements on which the Cartesian coordinate system is constructed is I and j, and R is a vector on the Cartesian coordinate system. Okay. Okay. So this is something. Now that means the basis here is 0 ket and 1 ket. Okay. 0 ket and 1 ket, and which means the alpha and beta are just like x and y. But the thing is, as we know, the quantum state should sum to 100% probability. Means the electron cannot exist anywhere else other than these two locations, which means alpha square plus beta square must be 1. So let's to have a resemblance, what I'll do is just take a unit circle where x square plus y square is equal to 1. That condition is there. All the points on the unit circle are actually resembling the quantum states on the left hand side. Now the thing is, on the right, on the unit vector situation, okay, there is a basis elements. If you just take a dot product between 1 to 1, I am getting 0. And if you just take a dot product between two opposite elements, I am getting 0. And dot product between I to I is 1, j to j is 1, I to j is 0. So if I have to have some operation between 0 ket to 0 ket, it should give me 1. 1 ket to 1 ket, it should give me 1. And 0 to 1, it should give me 0. Okay. So this is what required. Now the question is, what is that operation? What is this operation? Okay. So to satisfy this case, okay, there is a matrix interpretation was introduced. Okay. What is that matrix interpretation is? They called the 0 ket is equivalent to 1 0 column matrix. Similarly, 1 ket is equivalent to 0 1 2 by 1 column matrix, right? So which means the quantum state psi would be alpha 1 0 plus beta 0 1, which is going to give me a column notation alpha beta. Very good. Now, if you just see the length of the quantum state vector is alpha square plus beta square root is equal to 1. Okay. Norm is 1. Okay. Now I have brought in the matrix notation. Now, how do I have multiplication with 0? Because both of them are of same dimension. I can't have multiplication between two dimensions which are not suitable for the matrix multiplication. For that, what the people do it is, to have a proper multiplication, let's take the left-hand side entry as a complex conjugate and the transpose, which is called adjoint. Adjoint. Dagger is actually called adjoint. Okay. So when you take adjoint, the column becomes a row. Then it nicely allows me for the multiplication 1 by 2. I'm sorry. Okay. It becomes 1 by 2, 1, 0, 2 by 1, which is going to give me 1 perfectly. And similarly, operation 1, 0 with 1 is going to give me 0, 1, 1, 0, which is equal to 0. Okay. So the operations between the unit vectors of the basis elements of 0 and 1 is a matrix multiplication. The operation is matrix multiplication. Remember, the left hand side entry getting into the operation with the dagger acted on left entry of the operation element operation. Okay, that is very, very important. Okay, so having that, they gave a nice interpretation for quantum state being a vector, just like a two-dimensional vector in uh, a Cartesian coordinate system or a vector space. So they gave a name Hilbert space in which the quantum states are existing. Okay, the operation is matrix operation. Okay, and even they went on to describe the quantum states on a two-dimensional surface of a sphere. Okay, just like any 2D vector is having geometrical interpretation, in the same way, the vectors, quantum vectors are going to have geometrical interpretation. How? They introduced alpha as cos theta by 2, beta as exponential I phi sin theta by 2, where theta and phi are the blocks, the Cartesian coordinate system vector, and Cartesian spherical coordinate system. Okay, spherical coordinate system theta, and if this is a phi. Okay, so this, if this is a quantum state which makes angle theta with the k vector and makes its shadow, this is a shadow, its shadow makes a angle phi with the x-axis. Okay, so if you do that, you are going to get a quantum state with the cos theta by 2 0, okay, plus exponential I phi sin theta by 2 1 kit. Okay, and if you see, when you substitute theta equal to 0, means quantum state is actually pointing towards the north. And if theta is equal to pi, if you see, quantum state is pointing towards the south. Okay, any other values, any other theta and phi values would give you this superposition of 0 and 1. So that is how qubits are realized from the quantum states. Okay, right? So let me get back to my presentation. So let's say I want to realize a higher dimensional quantum system, not only just 2 bits. How do I do? I will take 2 qubits and interact them with each other. When I make them interact, they are going to, let's say, they are going to interact and they are going to generate higher dimensional memory locations. What is that is, it's just like I take 2 coins, right? If you toss 2 coins, okay? So higher dimensional, okay? Higher dimensional quantum memory, okay? Right? How they will do is, let's take an example, classical example, okay? 2 coins, okay? Coin 1 and coin 2. Okay, if I toss both the coins, tossing would result both coins to head toss, tail and tail. head and head. One of them tail, other one is head. Okay, so the 4 chances are there. Similarly, you take 2 qubits, qubit A and qubit B. Okay, so if I just take 2 qubits, the qubit A and B means qubit A could be in the ground, qubit B also in the ground, qubit A in the ground, qubit A in the excited at a given instant of time. Qubit A in the ground excited, qubit B in the ground. Both qubits can be in the excited at a given point. So there are 4 memory locations are created as 0, 0 cat, 0, 1 cat, 1, 0 cat, 1, 1 cat. So this is like a 4 element basis. Okay. Okay. 4 element basis. So if I prepare 2 qubit system, I am going to create a 4 element basis. So I will be able to store the information of 4 bits with the 2 atoms. Okay, like this. Remember the sum of all the alpha i's. Okay, let me write I here. I stands for 0, 0, 0, 1, 1, 0, 1, 1. Or instead of saying I, you can say X. It's easy. Is equal to 1. Okay. So, like in mathematics, if I want to represent the 2 systems bringing together, okay, tensor product is used. Tensor product describes 2 systems interacting. Okay. Which is, let's say there is a quantum state A and quantum state B is there. This is a tensor product. So literally saying, let's say quantum state A is written like this. Quantum state B, alpha B, beta. So which is going to give me alpha A, alpha B, beta B. Beta A, alpha B, beta B. Okay, which is gives me alpha A, alpha B, alpha A, beta B, beta A, alpha B, beta B, beta A, beta B. So this is what I am generating. This is like alpha 0, 0, alpha 0, 1, alpha 1, 0, alpha 1, 1. Okay. So this is how higher dimensional quantum systems are realized. If I want to have much more number, you just take 3 qubits. Okay. Okay. 3 qubits if you just take, let's say C, what you are going to get is 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, okay, 0, 1, 1. Okay. So how many? 3, 3, and last one. So there are 8 states possible, which is like 2 to the power of 3, the exponential increment in the memory. So if I take n qubits, we can store 2 to the power of n bits. Okay, it's exponentially large, right? So that is what, if you just take 150 qubits, it's very, very large number. It's enough to do large computing, like processing the atoms in the entire universe. Okay, very large memory. Only important thing here is all those few qubits should be ideal, should not be noisy, should not be disturbed by the surrounding. Okay, right? So let me get back again to the notes. Okay, so we have discussed this. Now we want to process that information, whatever is stored on the qubits. Okay, so how do I process that information? Yes, I can take this simple qubit. Okay, first thing I can do is just like a classical computing. Just The 0 bit is there, it is negated to 1. If 1 bit is there, that is converted to 0. Okay? How do? You act a NOT operation. Okay? So similarly, is there a NOT operation for a quantum qubit? Yes, there is a NOT gate. What that NOT gate does is it sends the 0 bit to become 1 bit, 1 bit to become 0 bit. What I mean is, okay, there is some transformation matrix, let's say M, which takes 1, 0, converts that to 0, 1. There is a transformation matrix, it takes 0, 1, converts that to 1, 0. By trial and error method, you can just guess what is this matrix, which is just something like this, which is called X gate, a NOT gate. Now, if you see a NOT acting on a quantum state, okay, what it does is, as you can see, it shifts 0 to 1 and 1 to 0. If you carefully see what it does, it is actually shifted the probability amplitudes of 0 and 1 gate. Okay, so the X gate interchanges the probability amplitudes. That is a very profound effect if you see. Okay. Now, what are the any other operations we can have? One more operation, interesting operation we can have is, if you just take a quantum state, alpha 0 ket plus beta ket, okay, I can change the relative sign between 0 ket and 1 ket, which is positive right now. I can change that relative sign into negative. What I mean is, I can convert this into new quantum state psi prime in such a way, instead of having positive sign, I can have a negative sign. So what I mean is, if you just take a quantum state representation, alpha beta here, beta alpha beta here. Okay, what I mean is, there exists a transformation matrix which acts on alpha beta, gives you alpha minus beta. Again, by trial and error method, you can easily guess what is this M, which is like 1, 0, 0 minus 1. Okay, right? So, yeah, right? So 1, 0, 0 minus 1. So which is actually called Z gate in quantum processing. Okay. Now the X gate and Z gate, if you carefully look, they're actually preserving the probability sums. Okay. What I mean is, the length of the quantum state before getting into the quantum gate is 1, and the length of the quantum gate after coming out is also 1. What I mean is, the inner, let's say there is a X gate, let's say a quantum state gets in, a quantum state gets out. What I mean is, the norm means the inner product, the length of the vector is 1 on the left hand side, norm of the length of the unit vector on the right is 1. So which means you can say, right? So the psi prime, inner product psi prime is 1, which implies, by the way, what is psi prime? Psi prime is x into psi. So if you replace this equation into this, what you get is psi prime x dagger x, sorry, no psi prime, it's just a, okay, x and psi. Okay, so this is equal to 1 means this is a quantity which should be 1. So that means x dagger x is equal to 1. Similarly, you can prove that z dagger z is equal to 1. Okay, so you can conclude that x and z are unitary operators. Okay, which means X inverse is just simply X dagger. Z inverse means simply the Z dagger. Okay, so this is the simple quantum gates which are going to act on one single qubit. Okay, now if I have a quantum state initially in the ground state, how do I convert that into superposition of ground and excited with equal probability? It is just like take a coin which is stable in the head and you just toss. During the flight, it is having a probability of both ground and excited. How to get that? That is a question. So in a coin case, you just flip it. But in a quantum system case, what you do is, let's say there is an electron in the ground strictly, you send a pulse of photons in such a way, one pulse will have so many photons. One photon puts the electron in the excited. It stays there for 1 microsecond. By the time it comes down, there is one more photon of this pulse, puts the electron back in the excited again. So this pulse of photon, what it makes the electron to make a oscillation between ground and excited. In that way, it is just like a tossing a coin. Okay, electron being excited and ground at the same time. Okay, so in this way what happens, we can go and create equally superposition state by just supplying pi by 2 pulse photon. Okay, so that's why it's called pi by 2 pulse. In fact, what it does is in the polar in your block sphere representation, if you just see if the quantum state is pointing towards the x-axis, sorry, the z-axis, it is going to be rotated about the y-axis with a pi by 2 angle so that the vector gets pointed in the x direction. Okay, right? Okay, let me change the color here. So this is pointing in this direction. Okay, so this is a pi by 2 pulse. Fine. So along the I, where is that block color? Yeah, along the I, along the J, along the K. So the pi by 2 pulse rotation is done by the pi by 2 area pulse. Okay, which goes and interact with the 0, put the 0 into superposition of 0 and 1. Okay, so along the x-axis, if we just take the quantum state is actually having 0 plus 1, both the contribution, it is comes from the north pole contribution, it comes from the south pole contribution as per our earlier quantum state interpretation of cos theta by 2, 0 ket, exponential I phi, sin theta by 2, 1 ket. Okay, fine. So now the question is, what is the quantum gate corresponding to this pi by 2 pulse? Okay, what I mean is, I am starting with the 1, 0. I will add some transformation matrix, which is going to give me 1 by square root of 2, 1, 1. What I mean is, this is 1, 0, 0, 1. Okay, so what is this transformation gate which gives me this? Okay, so in a reverse fashion, if you try, you can easily find out this m is actually 1, 1, 1 minus 1 with 1 by square root of 2. So this is called Hadamard gate. Okay, so basically in lab, it is correspond to pi by 2 pulse photons. Okay, and it is represented by H gate. Okay, so if you cross check whether H is a unitary or not, in fact, yes, it is a unitary. So you can conclude that all the single qubit gates, let's say X gate, Z gate, there is something called a Y gate is also there. what is the Y gate is, it's actually polymatrix. This is a X gate. So all of them and also H gate are unitary. This set is unitary. Okay, right? So these are like a single qubit gates. Now I want to process a multiple information, not just a one information. So we can have multi-qubit gates. Multi-qubit gates. Okay. So let's say I have one qubit. I have one qubit coming in. I have one more qubit coming in. I have to ensure there is an action on the second one depending on what is the level of information on the first. So what I mean is the first one is control, second one is target. Okay. Is there a gate like that? What I mean is if I send a 0, 0, there is a 0 here, there is a 0 here, there should not be any action on this. Okay. If I send a 1, but here I have a 0. If I send 1, 0, the control should remain, target should flip. Okay. Similarly, if I send a 1 here, if I send a 0, 1 here, okay. So what should happen? This one should flip. Okay. So this kind of a flipping is required. What I mean is quantum state input on some matrix should give me same state. Quantum state with the 0, 1 should give me same state. Quantum 1, 0 should give me the flipped state. Quantum 1, 1 should also give me flipped state like this. Okay. As you guys know, the representation for 0, 0 is the tensor product, which is going to give me this. Representation for 1, 1 is going to give me the tensor product like this. Okay, right? So what I want here is, I want to know what is this M. So M should not do anything for the control. So obviously these are like 4 by 1 matrices. So I will have M is also 4 by 1, 4 by 4. So there should not be any effect on the control qubit. So I'll put a identity. Okay. And nothing else on the second quadrant and the third quadrant, and X gate on the fourth quadrant. If you do this, okay, if you do this, in fact, this is going to act on, let's say, 1, 1, 0, 0, 0, 1. Okay, if you just cross check, it is going to give me 1, 0. What is that? So if you multiply 0, 0, okay, 1 and 0. So this is equal to 1, 0. So M acting on 1, 1 giving 1, 0. Perfect. We are getting that. So this is called controlled NOT gate. So even if you find the C naught multiplying to its C naught dagger is going to give me identity. So C naught is also unitary in nature. Okay, by now we can conclude that all quantum gates are unitary. Okay, or you can say all unitary gates are quantum gates, vice versa. Okay, we have another 15 minutes. We could quickly try to go through a few more things. Okay, so every gate is just like a rotation. In fact, the C naught gate is just like an exclusive OR gate. It's like an addition modulo gate. Okay, right? So C naught gate representation we just saw. In fact, if you see in a classical computing, all the gates are actually destroying the input and producing the output. So which means the output is produced at the cost of the input destruction. So that means I can never retrieve back what is the input from the output. So it's irreversible. But when it comes to quantum computing, if you just take any gate, Let's say there is x acting on 0 gives 1. You do one more action on x, it gives you 0. So what it means is x square is one identity and y square is identity, z square is identity and h square is identity. Okay, all the quantum gates you add twice, it will going to give back what is the input information, what is coming in the first place. So which proves that all quantum gates are reversible. That is a very good thing to have again for debugging the computations. If I understand that there is some error I made with the quantum circuit operation, there is something problematic, I can send the information back to the same circuit. I'll get back to the inputs. Okay. So in that way, quantum computing is more advantageous compared to classical computing. Now you can combine two quantum gates and realize a very interesting effect called quantum entanglement. It is being introduced to you all already. So what I will do, I'll just explain the implications of the quantum entanglement. So, for example, let me take a classical scenario. Okay, just consider a classical scenario. Okay, what is that is, okay, let's say there are two people, person A, person B. Okay, we put them together, make them interact with each other. After that, I separate them into two boxes without disturbing their nature, without fiddling with their thinking, and send A to one place, B to another place. Now, let's say I hit A and he feels sad. He feels sad. Now, if I ask somebody to observe what is B doing at the same time, interestingly, okay, B also feels sad. Even no one hurt, no one, no one, no one had hurted him. Okay. It is something which is difficult to accept in real world scenario. See, somebody has to do something, then only he feels sad. Na? Some kind of a telepathic thing is happening here. In a classical world, it's difficult to understand and accept. But when you do the same experiment at the quantum level, in the classical world, it doesn't exist. When I say two friends separated, if I do some bad thing happen for one friend, other five is also feeling sad. Not every time it happens. But when I take two atoms this time, okay, quantum domain, take two atoms, let's say qubit A, okay, let's take qubit A and qubit B, okay, let's say I'll put them together. Let's say both are in equal probable states. Let's say qubit A is 0 plus 1 divided by square root of 2. Qubit B is 0 plus 1 divided by square root of 2. When I put them together, they are going to create a tensor product. Okay. So what is the tensor product is 0, 0 plus 0, 1 plus 1, 0 plus 1, 1 divided by 2. All four states are equally probable. Now, by somehow, I can nullify the probability amplitude of 0, 1 and 1, 0. What I mean is, let's say probability amplitudes are existing like this. Okay. Somehow I can reduce the probability amplitude of these two to 0 and increase the probability amplitude of these two to higher values. Okay. And like the higher values, if I do, what is happening is I am going to get 0, 0 plus 1, 1 divided by square root of 2. So this is called a new quantum state is being created. What is that new quantum state? Now is psi AB. Remember, psi AB is not equal to, psi A tensor psi B, because two states are now gone. Okay. So in this situation, now you take this situation. Now let's say take a quantum state psi AB, which is 1 by square root of 2, 0, 0 plus 1 by square root of 2, 0. Oh, sorry, 1, 1. Okay. This is a quantum state I have. Now what happens? They are existing this quantum state, but physically we can separate them and put them into two separate boxes. Let's say there is an atom A in one box, atom B in another box. So physically separation doesn't mean the quantum mechanical separation. Okay? Physical separation means they still physically separated when physically separated. Okay? They can still possess the same quantum state, which is psi AB. Now I have this. Now, as per the quantum system, let's say a coin is being tossed. Let's say a coin is being tossed. Let's say a coin is there, which is tossed. During the toss, if you catch the coin, if you catch it, it falls to head. Means its flipping nature is gone. Similarly, if I have a quantum state, 0 plus 1 divided by square root of 2, if I catch the coin, it is going to destroy one of the probability amplitude, and the quantum state corresponding to the probability amplitude is crossed, and the system becomes a qubit state, single bit state 0. Same thing applies here. If I have a quantum combined state as 1 by square root of 2, 0 plus 1 by square root of 2, 1, 1. Okay. Now, if I make an observation on only atom A, if we make observation on atom A, if you make, let's say atom A falls to 0, implies the amplitude of 1 is destroyed. Okay, what is the amplitude 1 is destroyed? This one is destroyed. And remember, that is not only multiplied to just first atom, it is also multiplied to second atom. So what happens is, as atom A falls to 0 gate state, and simultaneously, atom B also falls to 0. This is due to measurement on system A. So this is what, even when things are separated, they're going to have the same effect. So without doing any information travel, the effect is traveled between two entities. So atom A falling to 0 ensures that atom B also falls to 0. Atom A falls to 1. Atom B falls also to 1. Okay. So this is how entanglement actually allowed people to have a long distance communication without communicating anything. Okay. So which is proved earlier across two islands. Okay. So there is one more thing I just want to show you. C0 gate variants we can have. We can have a swap operation between two quantum registers using multiple C0 gates. And we can have a controlled unitary gate just like a C0 gate. So using a C0 gate operation, you can realize a classical gate operation like a AND gate and NAND operations. And even fan-out operations you can have, that is already, I hope, discussed. Okay. There is something called in quantum systems, you can't clone the quantum systems. Why? Because if you try to clone, okay, if you assume the cloning is happening, it is going to give an absurd result by proof by contradiction, you can show that quantum systems are never possible to clone. So that is a no cloning theorem. Okay. Now, the quantum hardware is realized out of just like say electron revolving around the nucleus, and electron itself can have its own spin because of its rotation about itself. Similarly, nuclear spin is there, and there are so many other ways you can realize the qubits out of it. Okay. And so currently there is a qubits are realized out of a LCR circuit. Okay, these are called transmons. There is a trapped ion qubits. There is a photon based qubits are all shown here. There is NV centered qubits are also realized in the existing quantum hardware. Okay, when it comes to the mostly used qubits, realization is done by transmon. They are actually called artificial atoms. They're actually pure LCR circuits. If you just take LCR circuit, the capacitor can exist in multiple charge states. Okay, just like 5 coulomb, 10 coulomb, 15 coulomb or so. Instead of inductor, if you replace by Josephson junction, it becomes unequally spaced capacitor charge locations as shown at the bottom right. So, which is similar to real world natural atom. In this way, the artificial atoms are realized, which mimics the natural atom. Only problem here is to have a Josephson junction to work, which is made up of superconductor and insulator. The Josephson junction must be cooled to millikelvin so that it becomes a superconducting, and sandwich between, as there is a sandwich realized where the Cooper pairs are formed in one end of the sandwich and travels across the junction, that is an insulator, to other superconductor. So in this way, they create some induction effect. This induction effect creates unequal or non-linear energy separations or the charge separations of the capacitor. Okay, so this is how transpons are realized, qubits are realized, and there are so many applications people are trying to pursue these days. So some of them is quantum chemistry or computational chemistry, and biological applications like studying the protein folding and so on to designing a drug as per the proteins. And even for communication, people started using quantum key distribution, that is actually cyber security or quantum key distribution. So they are using quantum circuits and you can do quantum computing in much more faster. So that means you can do some good machine learning algorithms using a quantum hardware, which becomes a quantum machine learning. So wherever there is optimization task requires, you can use the quantum computing there. So for example, weather forecasting. Okay, so the recent opportunities is actually for the somebody to get in is quantum error correction, because all the quantum qubits were realized as of now are the noisy. How to tackle the noise? Some people can come up with the new algorithms. Okay, so you can start with the quantum algorithms and quantum cryptography and quantum chemistry, communication and sensing, and searching for a better materials for doing, let's say, carbon capture and other things. In that way, quantum material search is also done with the quantum computing. Okay, so there are so many great players, so big corporate players are involved in quantum computing. The leading would be IBM, and later on some Rigetti and from Canadian company D-Wave, and Chinese companies are there. So as of now, India is also playing its role through NQM. So I'll stop at this point. So let me summarize. I gave some quantum physics and some introduction of quantum computing, connect them together, and introduced some quantum computing understanding from the basic physics principle. Okay. So if there is any question, please do ask now.
Audience, please post your questions.
Yeah, please.
Participants, please raise your questions. Or else you may post the questions in chat window.
Thank you very much for listening to me. If you have any questions, please you can share the your question by mail, and the organizers have my email ID and my phone number also. So why can't we clone a quantum states? A very good question. Okay, right?
Yes,
Yeah.
sir.
Yeah, why can't we clone a quantum system? So let me prove that by contradiction. Okay. So let's say I starts with the simplest qubit, so simplest quantum gate. Let's say it does a cloning for us. Okay. Right. So let's say take a C naught gate. It takes a 0. You send a, it will give 0, 0. Very good. If you send a 1, 0 as an ancilla, it gets you 1, 1. Very good. I am able to clone 1, 1, right? So which means, let me try to put a superposition state 0, alpha 0, and beta 1 as a control, and try to take an ancilla 0. Okay. So what is the output here is, okay, whenever, so the input at this point is alpha 0 plus beta 1, okay, and 0 tensor. This is the input. Now on that I have a C naught gate. So what is the output is alpha 0, 0 plus beta 1, 0. Okay. So this is a C naught. So whenever control is 0, target should remain the same. Whenever control is 1, target should shift. Okay. So this is the output. I am started with the some quantum initial state. I got some quantum state 1. Okay. Now, is it cloned version? That is a question. Okay. Because it was cloning earlier. Now, we assume that when I send a superposition, I got some output. Now, the question is it cloned? Okay. Now, what is meant by cloning? Let's say I have a box. There is some quantum gate, unitary gate. If I send something, okay, let's say I send some quantum state. If there is an ancilla 0, I should have the quantum state here and also quantum state here coming out. Okay. Now, what is my psi? Why my psi is alpha 0 plus beta 1. What is the psi here? Alpha 0 plus beta 1. What is the psi here? Alpha 0 plus beta 1. So this is a cloned scenario. Okay. So what is the input? Input is size tensor 0. Okay. What is the output? Output is psi tensor psi. Let me write down what is the output. Output is alpha square 0, 0, alpha beta 0, 1, beta alpha 1, 0, beta square 1, 1. This is the output. But if I assume that there is some gate which does the cloning, this is the output. But what is the least possible case? The C naught gate which was able to clone single bit states. If I use the C naught gate to clone the superposition state, what was I was getting? I was getting, so if I assume cloning is possible, okay, what I am getting? Output state I am getting is alpha square 0, 0, alpha beta 0, 1, beta alpha 1, 0, beta square 1, 1 I am getting. Okay. But what is the actual scenario? What is the actual case? Okay. Actual case is quantum output state is alpha 0, 0 plus beta 1, 1. This is what I am getting output. Now, to make cloning possible, the real world scenario must be same as the assumed scenario, cloning scenario. So, the both are equal only when alpha square is equal to alpha, beta square is equal to beta, alpha beta is equal to 0, beta alpha is equal to 0. So anything in any number system, if you take, would not satisfy the above case. Okay. The obvious cases are there. What are the obvious case? One of them is 1, other one is 0, the obvious case. But we don't want that case. We want a superposition states to be cloned. That means the assumption of cloning is possible is not. So that's a wrong assumption. That is why cloning is not possible. So in the physical interpretation, if I have a qubit which is oscillating with some frequency, some oscillation theta and phi, we can't exactly clone that to another one with the same theta and phi. We can destroy this theta and phi, take theta phi value from there and clone it and prepare one more with the same theta and phi. That is possible, but not at the same time. So that's why cloning is not possible. Okay, so there are questions. Let me see quickly. Okay, so right. Okay, sir, can you please? Okay, after the cloning, we can't. Okay, after the cloning, what are the suggest few textbooks for quantum cryptography? For quantum cryptography to start with, I think you can start with Nielsen and Chuang itself as a nice chapter on the quantum key distribution, the fundamentals. And from there on, you can go on to, I would suggest to read the articles on quantum BB84 protocol, the actual protocol, the journals. Okay, they are the very good means. Okay. And okay, next question. How do qubits differ from classical bits using superposition and entanglement? See, classical bits, as we can see at a very, very long earlier. Okay. Okay. Where is the description? Here you see, classical bits are fixed. They are not going to change. Thus, if I am going to arrange the bar magnets towards the left direction, they are 0 bits. Okay, the bar magnet is not going to flip, it is going to be fixed. So certainly they're existing with 100% probability in the same state. That is a classical bit for you. But when it comes to quantum bit, the quantum bit is like superposition of electron being existing in multiple locations or multiple orbital location at the same time. Okay, that is with the probability. Okay, so that is what the quantum qubit is. That is how the quantum superposition state is different from classical scenario. Okay, so when I can have two qubits entangled and merged together in so much, if they end up with a quantum qubits, the quantum entangled state, which I was showing here. So this is a bell pair. In that case, they're said to be entanglement. Something happens to one guy, forces the other guy to undergo the same change. That is the quantum entanglement for you. So what are the core principles of quantum computation? Like superposition entanglement, how do they enable quantum computation? So how they enable is you take the one advantage with the quantum computation is you can take all the possible states, put into a superposition and study them in one shot. So that is how quantum parallelism is actually coming. Okay, so along with that, there is a possibility of probability amplitudes also interact with each other constructively and destructively. That leads to a nullifying of probability amplitudes, and in fact, that is what lead to entanglement. Okay, so in this way, parallelism with the interference gives you a nice effect called exponential speed up in finding the let's say if I have a task, we want to find the solution of the task. Okay, so you need to assess various scenarios. All those scenarios in one shot you can assess and you can get the answer. So that is how exponential speed up is giving you the birth of quantum computing or the quantum computing applications. This is how quantum entanglement and superposition enables the quantum computation. Okay. So what are the major applications of quantum computing in the fields like drug discovery and material science and optimization? So in the drug discovery, see, there is a protein, bad body is bad about proteins. So how the proteins folds, depending on the folding, they have a particular function to do. So finding various ways of protein folding as a different functions associated with the protein. If there is a protein problematic, there is some issue with the folding, so we need to correct that. So to correct that, first we have to understand how it is folded. So to finding a protein folded, it is not that easy because there are so many parameters. For example, if you just take amino acids, there are so many carbons, okay, they're arranged. Those things must like interact, and the interaction should be understood. So for that, you can't use a classical computing. You have to use a powerful quantum computer, which takes all of the parameters of many carbons there and their electrons and allow somebody to study it. That is how the drug discovery could be much more quick fashion you can do by studying the protein. In the case of material science, like I said earlier, we have to prepare some kind of a carbon capture material. Or there are some alloys I want to find to particular experiment or particular application. So I have to prepare. So which combination gives a optimal result? I can't just do experiment. I can't do that. So what I do a simulation. Classical computer is unable to simulate various combinations, billions of combinations, but quantum computer can do. In that way, in a material science, you can search a better material with a more quick time using the quantum optimization algorithms. Okay, right? Thank you for the question, Harshita. Okay. So there is what are the primary challenges facing quantum computing, such as decoherence and the fragility of quantum states? So decoherence means the quantum state being not quantum for a very long time. Okay, because of the environment. So the quantum qubits are so much fragile, they interact with the the environment, and takes the temperature from the environment. So even a room temperature is enough to destroy the quantum qubit. That's why the transforms has to be cooled to millikelvin to avoid the outermost environment interaction. Okay, so decoherence is a big problem. That's why people enclose the qubits inside a cylinder and cool it to millikelvin to avoid the external interaction. Okay, so that is one way. Another one way, we can take a robust qubits like NV center inside a diamond, solid state uh, qubits, where the external magnetic field and electric field may not have influence on the qubits, which are all the way inside the carbon structure in a diamond. Okay, so there are problems with the decoherence. There are errors coming because of that. People are coming with error correction codes like a Shor error correction. So in that way, existing noisy quantum computer and qubits could even allow us to do some computing much faster than classical computing. Okay, thank you for the question again. Dear professor, please post your question to the resource person mail ID. Yeah. Please clarify how
Yes.
the artificial atoms function in the quantum hardware. Okay, so artificial atoms, just like in my slide earlier. Okay, quickly I have gone through. If just to see on the right side, there is a LCR circuit. Okay, inductor is there, and okay, let me quickly draw. Okay, so if I have, okay, if I have an inductor, if I have a resistor, if I have a capacitor. If I just take that and add a battery. So what I will see here, capacitor is charging between, let's say 0 coulomb to 100 coulomb, and it oscillates. It oscillates. Okay. So this is how oscillator I can create. Okay. Electronic oscillator. Okay. I can tweak the inductor and the capacitor in such a way. So I'll have an inductor and I have a capacitor, just like here. Okay. And I can have an oscillating input. Okay. I can have oscillating input, okay, voltage, and then ensure that I will have a capacitance being charged, let's say 0 coulomb, 5 coulomb, 10 coulomb, and 15 coulomb. It can exist in any of these possible states. So you see all of them are equally separated. Okay. If I try to say they are quantum mechanics states. If I try to realize any two states as a qubit, there is a chance the information is leaked out to the other two states which are equally separable. Okay. Equal separation. For that, what people thought, they replaced the inductor with Josephson junction, okay, and then use the same oscillatory field. And if you do this, what happens? The separation becomes 0, 5. The next one is 7. The next one is 8. And so on. This is become unequally spaced. This way, I can realize a qubit out of it. Okay. So Josephson junction to work as an inductor is a superconductor and insulator and then superconductor. So if you have this, superconducting means what? Superconductor creates a Cooper pairs. When you cool to millikelvin, there are electrons combined, they become so far, super powerful, they can travel without any resistance. So the Cooper pairs form, they travel in such a way, they go through the insulator and they comes back. They make an oscillation between them. So there is an induction effect of travel of electron between these two. That is why they act like an inductor. So when they act like inductor, this kind of unequal energy states are formed. So unequal energy states are just equivalent to having the natural atom. That is what's shown at the top right. So this is how they are going to realize a qubit out of it. Okay. So this is how artificial atom function in the quantum hardware. So the circuit which I was shown here, this is on the left. What you see, there is a qubit 1, qubit 2, qubit 3, qubit 4 is actually having Josephson junction, and the capacitors are arranged in a zigzag manner. Why capacitors are arranged in a zigzag manner? To have a better capacity. So the capacitance plates are arranged like this. If this is the area is there, capacitor area is there. Okay. Okay. So the capacitance is actually connected to area, right? Okay. So to have a better area, what people do is they will have one plate arranged like this, another plate is arranged like this. Okay. So zigzag manner, there is a lot of air space could be created between two plates. So that is what you see here in the quantum transmons. Okay. Right. This is how quantum qubits work. Any other questions?
Thank, thank you, sir.
Yes,
Our
yes.
heartfelt thanks to Aswath Babu, sir, for conducting the insightful session on Introduction to Quantum Algorithm. Your expert guidance, clear explanation, and passion for the subject have made a complex topic accessible and engaging for all of us. Your willingness and involvement to make the schedule of this FTP answer our questions, provide real world examples, and share your wealth of experience has not only deepened our knowledge but also inspired many of us to think critical about how we can contribute of this engaging field. We truly appreciate the time and effort you have dedicated to enriching our knowledge. Thank you for inspiring us explore the existing world of quantum computing. Thank you, sir. Thank you so
Sir,
much.
sir, one question actually. Can you please suggest some textbook on this, sir?
Yeah, the textbook is the best textbook is Nielsen and Chuang. This is a book. So quantum information, confirmed science and technology. I think it's a Nielsen and Chuang. Nielsen and Chuang. This
Thank you,
book
sir.
is Nielsen and Chuang. This book is available in the net. Okay. So I can show you how this book looks like. Okay, let's give me 1 minute. Okay. If you just check, okay, just a minute. It looks like okay, 1 minute. Okay, it is quantum information science and technology. Nielsen and Chuang. Nielsen. It is available in the net. This is a book you can download. Okay. Yeah. Quantum computing and quantum information. This is a best book, and there is some book called Quantum Computing and Information, I think Millman. So that book is also good. I use this book. This is it's in a way kindly like kind of a Bible. So you
Thank
people
you,
can,
sir.
yeah. Yeah. So
Thank you
once
so
again,
much, sir.
thank
Yes.
you, Narayan sir. Thank you very much for the opportunity. I
Thank you,
hope
sir.
the audience got something out of it. Okay. So I was able to connect quantum physics and quantum computing and brought some sense into it. Okay, there is a question here. Here. Uh, how qubits leverage superposition and entanglement for complex calculations? How different hardware types achieve these states? And the potential to revolutionize industries like cryptography, drug discovery, AI through solving problems, and interactive for classical computers. So once like your question itself is having answer, qubits are actually superposition of multiple states. So adding so many qubits, you can take a superposition of multiple combinations. In that way, if there is a task which requires to study so many individual scenarios, all those scenarios in one shot I can study by feeding to the computer, that is a quantum computer. I can create a superposition state. I can study them in one shot because quantum computer allows that through superposition. By adding entanglement, we can connect each superposition state substate to other state and have an effect in such a way we can eliminate unwanted states, unrequired scenarios. Okay, so this is what quantum computing with the superposition entanglement offers us to even do a complex calculations where a lot of memory and lot of processing is required, which could be bypassed through quantum hardware. Okay, that is the answer for your question, Arshita, once again. Thank you for the question. Okay, so I hope there is one more session after this, I guess.
Yes, sir. We have
Then
one more session, sir. Thank you for your interest, and the participants are make a more involvement for your session, sir. It might be crossed more than 1.5 hours, nearly 2 hours. We crossed the session, sir. It was a more interesting. We thought that we are sitting inside the classroom, how the students are listening. That kind of way you are handling. Thank you so much for your participation on this, sir. Thank you, sir. Now
Okay.
I'm inviting that resource person, Dr. Navin Kumar Adesan. He is a professor and head of the Department of Computer and Communication, Nehru Institute of Engineering and Technology, Coimbatore. He completed his BE ME in the year of 2005 and 2007 onwards, and he earned that PhD degree in the year of 2017 from Anna University. He is a specialization of optimized text categorization. He published more than 18 journal papers and nearly attended 20 international conferences, and he completed a patent in the number of 7. He is having a membership of CSI, Computer Society of India, ISTE, and Indian Sciences. He has authored a book title From Foundations of Data Science and contributed 3 indexed book chapters. Moreover, that his research interest includes on machine learning, bioinformatics, network security, data mining, cloud computing, optimization, and quantum computing. With this, I conclude and I invite Dr. Navin Kumar going to present the session. Navin, sir? Navin, sir? Navin, sir, am I audible? Navin, sir? Navin, sir is going to start her presentation. Sir, am I audible, sir? Are you able to hear my voice, sir? Navin, sir? Sir, mute yourself, sir.
Is it audible, sir?
Yes, sir. Now you're unmuted.
Sir?
Yes, sir.
Narayan, sir?
Sir, yes, sir. Your voice is audible, sir.
Sir, audible?
Yes, sir.
Hello?
You're audible,
Sir,
sir.
audible? Okay, fine. Okay, fine. Screen sharing, okay?
Yes, sir. Yes, sir.
Okay. Okay, fine, sir. Thank you.
Sir, you start your presentation, sir.
Hello? Is it audible?
Yes, sir.
Dear participants, happy morning to all. Sorry, happy evening to all. Let us start today's session. Is it audible?
Sir, yes, sir. You're audible, sir.
Yes, sir.
Hello? Ma'am, is it audible, ma'am?
Yes, sir.
Hearing us, sir. On the side, the voice sir. No problem. Okay, let us start. Okay.
Yes, sir. Yes, sir.
Voice breaking, immediate call, sir. Thank you, thank you. Once again, dear participants, happy evening to all, and thanks for giving me the opportunity to for organizing team, particularly Nitya ma'am, Rajanarayan sir, Sendil Kumar sir, and all of you. Once again, thanks. Today I am taking the topic about the ATAL FDP program, quantum state algorithms. So let us start a quantum state algorithm. Before that, why we want to go for a quantum state algorithm? What the quantum machines has to perform? Let us see this. Sorry. Sorry. Today, sorry. Oh God.
Just now it was coming full screen, sir.
Sorry. Slide is slightly moved. Few minutes. So the slide. Sorry for the inconvenience.
Sir, open your PPT in the full screen mode, sir, and then you share the window.
Little network issues. Okay. Okay, okay, friends. Let us start today's topic. Before quantum state algorithm, let us start from why we want to go for quantum state algorithms. Before, all of you know that quantum computer right now. Why means it's a fastest computing operations can perform by the quantum computer, it will be comparatively supercomputer. Why we have to classifying now? Let us tell. Quantum computer is nothing but is a machine that performs calculation based on the law of quantum machine mechanics, which is behavior of particles at the subatomic levels. It's
Sir Naveen,
called
sir.
quantum computer.
Sir
So
Naveen, sir.
let us know what quantum computer.
Sir Naveen, sir.
That's a thing we are approaching from that quantum machines. Now let us make it classified to these two things: classical computing as well as quantum computing. What the classical computing faces right now, the problems can face it. Looking into this, the large scale optimization and cryptography is a
Excuse
major
me, sir. The
factors
screen is not
for
visible.
problems can occur from this classical computing right now. What the optimization means,
Sir Naveen, sir.
that these three factors is a generally we have to approaching from this classical computing problems: exponential time and memory.
Excuse me, sir.
Hello, sir. Sir, is it audible, sir?
Sir, the screen is not
Screen share
visible.
आएगा, sir? Sorry. Okay. Sir, ஆயிடுச்சுங்களா சார்? ஸ்க்ரீன் ஷேர் பண்ணிருக்கேன்னு நினைச்சேன். வெயிட் சார். ஸ்க்ரீன் ஷேர் ஆயிட்டுங்களா சார்? இல்ல சார், இப்போ நெக்ஸ்ட் சார்.
Now we are seeing, sir.
Full review, full screen மூடுங்க சார். Yep. Sir, once keep it on, sir. Sir, that slide.
Now it is full screen, sir.
Change it, sir. So slide changes now. Change it, sir. Changing. Okay, fine. So
Yes, sir.
fine, sir. Thank you. Yeah. Okay, sir. So make it clarifying this quantum computer, then follows to that classical computing means this is the large scale computing, large scale optimization and cryptography as a major factors for right now the issues occurring into the real time. What are the factors we have to concentrate on both the optimization technique means exponential time and memory, then poor scalability. So why we tell like that means we know all of you that AI machines, AI operations, how the system has to backend to perform. All of you know this, the machine computing, how machine learning process, what are the data, how much data has used to do backend to perform. Everybody know about this. That's the thing. The classical computing facing this, that optimization, the large scale optimization, it's a major factors as occurring to the problems. Then this is the three factors. One is exponential time and memory, then poor quality, so poor scalability. Cryptography, security relies on hard problems, high resource uses. So we facing into that common problems means that real small scale issues or whatever the solvable problems can use from that cryptography can use from this easily to solve that classifications. But it's used from this toughest problem means it will be the any threats, hacking or any threats can occur means that highest problems, it will be used from this highest resources can solve the problem, solve the issues. This is classical computing phases in current scenarios. Then quantum computing offers exponential or quadratic speedup. This is main factors. What are the things happen into this quantum computing? All of you know this: fastest computing operations. Its quantum algorithm exploits the three tools that are used from this: superposition, entanglement, and interfaces to process many possibilities in parallel. what you mean, all of you know this zeros to 1. As a classical computer, zeros or ones or 0 or 0, whatever that combination only can perform. But 0 and 1 in between, the process has made up of this quantum computing process, that is qubit. The superposition as qubit exists in 0 and 1 states simultaneously. That simultaneously means not only yes or no. This true or false statements as performed by the classical computing. Why I clarifying these two difference means classical as well as quantum. Quantum made up of this, that combination of zeros and one bits as to perform by the superposition of the computers. That's the main thing. Then entanglement. That entanglement is it's also made up of this strong correlations even at a distance is used to perform. Interferences is nothing but quantum states combined to amplify correct results and cancel the errors. So automatically all operations, all combination of problems and solutions as generated by the quantum operations. This is a thing, the three factors as performed by the quantum computing operations. Then let us, what are the advantages as used from this quantum state algorithm? You just look into this core enablers. The quantum hardware provides the platform, but it's algorithm that unlock true computational power. You just think about this, whatever the concise, whatever the calculations before, automatically the runtime, the operations will be made to this combination of results as to generate it. This core enabler, what made up of this, unlock the true computational power as to generating by the solutions. Then efficiency gain. Efficiency gains, quantum algorithms reduce the complexity. So automatically the complexity issues has to be reduced. How it is means exponential via the polynomial, then linear to square root. So these are the mathematical functionalities should be improve the gains, improve the efficiency from the quantum algorithms. Then what are the breakthroughs as to do for this? What are the issues? Shor's algorithm as factorization problems, factorization issues can sort out from this Shor's algorithm. That Shor's, in 1994, the Peter Shor has invented this algorithm. As after that, what are the applications as used from this? We will see in later. But before, we have to summarize these things. RSA and public key cryptographic system as to use. Grover's algorithm. The Grover's algorithm is nothing but quadratic speedup in database search problems. Grover's algorithm is nothing but search problems, searching problems searching issues, searching applications and use from this Grover's algorithm. Then domain specific advantage. Tailored algorithm bring advantages of optimization, simulation, cryptography, AI and drug discovery. All aspects as used from this algorithm. Okay. Then scalability factor as used from this algorithm determined by the quantum advantages in practical form as hardware scales for scalability factors as improving the quantum operations as well as applications solutions. Innovation driver. Ongoing research in algorithm expands the scope of problems quantum computers can solve. Okay, so what are the main thing? The scalability factor as well as innovation driver as main theme of solve the all complicated or complexity issues will be sorted out. Basics of quantum computing. So let us look into this. Qubit is a basic unit of quantum information that can exist as 0, 1 or both at once through the superposition. We have already concise to the bits along this zeros or ones only can perform by the classical, classical computing. But here we are using from this zeros and ones, 0, 1 or both at once through superposition. Okay, so these are the things happen into this qubit. Superposition, qubit is multiple states simultaneously. Look into this. Here the process 0 plus 1. The both qubit as combination of 0, 1, 1, 0, 0, 0, 1, 1. So the minimum, the 2 bit as to combination of 0 to 2 to the power of square. Okay, so this is superposition factors. Entanglement, that entanglement as used from this linked qubits. That linked qubits means strong correlation between these 2 bits, correlation between the between the qubits. Then Bloch sphere is way of the sign we can use from this continuous process as used from this model. Here as a visual model of a qubit. Visual model means we have to graphically representation from these this applications and show from this results as a visual model. Quantum parallelism enables solving complex problems as then Foster. Okay, then what are the quantum state algorithms as to be classifying here? Here, one thing, algorithm that manipulate, evolve, and measure quantum states. The four key points as you used to do made up of these quantum state algorithms. First point, it's manipulate, evolve, and measure the quantum states. These things we will be seeing later in the further slides. Then the second key point, used for search, optimization, simulation, and factoring. Bridge between mathematical models and quantum hardware. Foundation for Groover's, Shor's, and quantum phase estimation. So let us look into this. Manipulate and measure the quantum states as within this within the circle we have used from this qubit process. Then applications from the search and optimization from simulation plus factoring as used from this kind of process. These pictorial representations can try to explain those 4 states, how we have to do exploring the results. Algorithm that manipulate, evolve, and measure quantum states. Quantum state algorithm. See the previous slide. The quantum state. What are the quantum state algorithm? How I have to define these 4 stages, 4 steps as to do for extended to the quantum state algorithms. So let us look into this algorithm that manipulate, evolve, and measure quantum states. Quantum state algorithm control the evaluation of qubits through superposition, entanglement, and interference. So these are the factors as used from this quantum state algorithm. How to define from these quantum states? Initialized, transformed, and measured. Provide the rule set for performing computation on quantum hardware. So the rule sets how to fix into this. Based on that, we fix into the conditions or rules, and whatever the policies will be made up of this policies based how to perform by the quantum operations. Then example, rotating a qubit on the Bloch sphere to explore multiple states simultaneously. Why? We already tell about this, that the qubits has to define to that multiple states. Multiple state means 0, 1, and both zeros and ones has to use to made up of these functions. Then applications in search, optimization, simulation, and factoring. The search as already told about this, the Groover's algorithm gives quadratic speedup in unstructured databases. Then unstructured databases as used to do for the functioning. So make it clear, the Groover algorithm as a purpose of this searching the data basis from this what category of data also can use from this search in the process. For just for this examples, what we can call now right now this like a lot of unstructured data means the texture or textual data. The text data means the text data can use from this searching process. Optimization, quantum approximate optimization algorithm improves the large scale decision making. Large scale decision making. Then, as a simulation, models molecules and quantum systems beyond classical limits. Example, we use from this wherever we are approaching. Already previous session, the SAR also told us for many chemical reactions or material science also, we are using from this quantum applications as performed. So according to this, the simulations also, molecule models and quantum system for classical limits based on that constraint about the any material meaning products you have to fixing into this. Then factoring as a performed by the Shor's algorithm. Peter Shor's algorithm efficiently factors large integers impacting cryptography. Large integers and impacting cryptography. Right now, that cryptography, that RSA and public key cryptography systems, all those cryptographic algorithms we are using from this Shor's algorithm. Then each application highlights practical quantum advantages. So all the algorithms can use from this currently what the complexity issues we can apply in the problem, applying the algorithms. Bridges between mathematical models and quantum hardware. Quantum algorithms translate theoretical model. The theoretical model, how we have to do from this. So linear algebra, Hilbert space into the physical instructions. So let us see here the quantum algorithm, how to translate from this theoretical model means these two major areas has to covered by the quantum approach. Yes, physical instruction means physically we have to give the in all kind of instructions as per the quantum quantum bits, quantum entanglement, everything we have used from these factors can use from this the linear algebra as well as Hilbert space used from this operations. They adapt to real world hardware constraints like noise, coherence, and limited qubits. So that we are using from this real world problems means looking into this. We are thinking about this some noises and any audio noise, audio or wherever it is. We have huge data can process huge or huge community or what can we say the huge crowd or anywhere we can use from this real world issues can sort out from this quantum hardware can scattered as well as filtered into the right things has to given into the source of applications. Then act as a translator between high level quantum theory and low level machine operations as made up of this translator as used from these operations. That one kind of hardware, what have to transmitting means high level quantum theory and low level machine operations. So why we are using right now as our classical machines as quantum logic, quantum things, quantum operations can convert it into that low-level machine operations as to do for the quantum translators. Ensure that quantum computing moves from abstract model to practical execution. Practical executions. Then let us see this. Let us see this. Foundations of Grover's, Shor's, and quantum phase estimation. These are the main quantum state algorithms. As a Grover's, we know that it's a searching. Shor's as a RSA and factorization problems can sort out from the Shor's algorithm. Then quantum phase as a core quantum simulations and eigenvalue problems can sort out from this quantum phase estimations. Then to be represent the starting point of future breakthroughs in optimization, AI, and secure communication. Right now, where they have used from these all kind of operations, all kind of algorithms directly to involve into this artificial AI, and as well as secure communication means cryptography levels, cyber security system as used from this that quantum algorithms as approaching. Bridges between mathematical model and quantum hardware. So here, all of you know this, the quantum machines where they have to backend of resources from this mathematical applications. That mathematical calculations as directly involved into the quantum algorithms. So look into this quantum algorithm, translate theoretical model, linear algebra, Hilbert space into the physical instructions. So I think this slide has already seen into this. Then foundations for this building blocks. Starting point of already looking into this mathematical foundations. It's direct notation. It's direct notation is a bracket symbol, bracket notations as used from this quantum states. So this quantum states little descriptive problem describe the theoretical notation. Theoretical wise, direct notation is a bracket notation. Bracket notation means that symbol as defined as bracket notation is a standard notation for quantum mechanics. It's introduced. Who is introduced? Paul Dirac as to represent the quantum states and operations made into the consistency to be prepared by the Dirac notations. Okay, Dirac, who has developed by the process means Paul Dirac. Paul Dirac means he is one of the person has to do invent to the quantum states and operators consistently to make do that Ket notations as used. State vectors. That state vectors is nothing but linear combination of 0 and 1. Ket 0 as well as Ket 1 notations as used from this process. Then that Ket vector, that Ket vector is equal to 1 plus 1 Ket by square 2 root 2 square. Okay, 2 root of this value. Density matrix for mixed states. Density matrix for mixed states. Then linear algebra as well as probability are central tool of this all the quantum operations. So let into this what we have to know about this quantum mechanism, quantum algorithms, which mathematical area has to covered by the process means linear algebra as well as probability as main vital role of define the quantum algorithms. Okay, wherever you have to take whatever the algorithms as backend of this linear algebra as well as probability as main impact from the algorithm solutions. Okay, what we have to do that Ket vector, how we have to represent it from this quantum states. The quantum state purpose of Hilbert space, as well as what another one of think concisely, we have to make it to the quantum state operations. Okay, then quantum gates and operations. Hudmore gate as to create the superposition value. Create the superposition value. Pauli gates is not three variable as used to this rotation around Bloch axis. That Bloch axis also how to do for the process means xy is that axis where we have to do concise from the problems. Okay, C not gate as endangering operations. All gates are unitary operations, is reversible process also, reversible operations also. Building blocks of quantum circuits. The quantum circuits, how I've explored this all the mathematical notations as well as quantum gates via we will build the quantum circuits will be get into the accurate results as well as optimized values also. Core algorithms. For first of all, the Groover search. The Groover search as problem of search unsorted database, unstructured. Already told about this. Groover's algorithm is a search algorithm. The search algorithm, what kind of database has to function it? Unstructured databases of n items. As within n items, we have to find out that accurate data, accurate value has to pick into the searching process. How? You just think about this. The Groover's algorithm as a quantum search algorithm. It's made up of this classical search as well as Groover search. Classical search, what to do? Order of n, time complexity as performed. Order of n time complexity used from this classical search. As a classical search, we all of you know this regular computing search we are using from this order of n. Quantum search as a order of root to the power n root. Okay, so this quantum search as used from this kind of queries as well as quadratic speed up used from this quantum approach. Quantum approach is what have to do this quantum. This is a quantum search or otherwise Groover search. The Groover search is impact to the quadratic speed up. Quadratic speed up means all of you know this. That's the speed up, as we know all of you, that all combination, all possibility of values has to combine. And what combine means, what we have to do mapping together to getting into the accurate results. What means huge unstructured, unsorted database has functioning by the quadratic speed up via the Groover search has to approach. Then amplitude amplification. That amplitude amplifications, what as used from this Groover's diffusion operator. Groover's diffusion operators as used. That operators, how we have to do that amplitude amplification as a probability amplitude of target states. The target state has to fixing into that amplitude amplification. That operator also we are using from this direct notations. Direct notation means get vector as used to do for calculating the operations, entire operations. The key advantages as quadratic speed up. Already I told about this. The quantum search as concise to the quadratic speed up. That's important thing. Then applications, optimization as well as cryptanalysis. Okay, so where we have using from this that complexity problem, that high complexity issues can solve through this optimization as well as cryptanalysis via we have to do giving it to the right solutions from the problems. Okay. Then core algorithms, that second algorithm, Shor's law, and as well as QBE. The Shor's algorithms is it's a kind of a quantum algorithm for integer factorization. First of all, integer factorization in polynomial time. Okay, so the factors also the large integer factorization using into that polynomial time SHA-2 function. Then breaks RSA based cryptography. All of you know this RSA algorithm based the cryptographic issues can sort out from this Shor's algorithm. Okay, then efficiently that Shor's algorithm, particularly the factors large numbers of n, breaking the classical crypto system like RSA. So classical factoring means exponential time. Shor's algorithm means what? So make it clear about this classical factoring. Each variant have to make difference between this classical as well as quantum. So classical factoring, exponential time based on that processing have to perform. But Shor's algorithm as used from this polynomial time. Used from this polynomial time. Shor's algorithm have to approaching this polynomial time. That polynomial time also how have to do calculate what they have to formula has used. Order of log n to the power of q is using from this polynomial time. Okay, so this is Shor's algorithm polynomial time. What are the steps as used from these Shor's algorithm? Classical preprocessing as well as follows to that quantum period finding, then classical post-processing. So these three steps as used from this Shor's algorithm. Okay, make it clear about this that before this Shor's algorithm, wherever we are using from these process means, once again I clarifying that it's a quantum algorithm for integer factorization. It's a large number of factors using classical crypto system like RSA. Okay, then classical factoring, it's an exponential time as to functionating the entire operations. Then Shor's algorithm is nothing but polynomial time. That polynomial time, how I have to calculate it through this kind of notations. Order of log n to the power of q is using from this polynomial time for Shor's algorithm. Then the steps, the three steps as used from this Shor's algorithm. One is classical preprocessing. The classical preprocessing as well as we are using the what kind of random number as used from this find out the factors. Then quantum period finding. Quantum period finding is a second step of this Shor's algorithm. It's what quantum circuit to find a period or of the function x is equal to a to the power of x mod, and this is the periodic finding factor formula. That periodicity is nothing but we can calculate as we note it here formula only. So I try to convey that formula, what formula is using from this particular step. I'm trying to tell you, but I not define from this presentation slide due to time factor. Periodicity is nothing but x plus r is equal to f of x. This is periodicity. So these formulas were the second step of quantum periodic finding using from this formula. Classical post-processing, if r is even, compute GCD, then returns non-trivial vectors of n using from this classical post-processing. Okay, so what are the key points we are conclude from these Shor's algorithm means quantum Fourier transform for period finding, then efficiently factor numbers exponentially faster than classical methods. that particular impact to be done by the Shor's algorithm. Threatens RSA and other classical cryptography used from these source algorithm can sort out the problems. Okay. Then quantum phase estimation. That quantum phase estimation, all of you know this. These quantum bit errors or quantum errors can sort out from these quantum phase estimation. Estimates eigenvalue of unitary operators, foundation of chemistry, simulations of QML. Okay. So that we can define as quantum errors. Type of quantum errors means bit flip error, phase flip error, and bit plus phase flip error. So already we look into that one statement, x, y, z factor. X, y, z means x is x error, z error, and y error. How I have to do calculate it means bit flip error, phase flip error, or as well as bit plus phase flip error. Using from this type of quantum error as to define from these operations. So then into this emerging and hybrid algorithms, variational quantum algorithms. Then follows to that VQE, variational quantum eigensolver. VQE means QAOA, quantum approximate optimization algorithm. Combined quantum and classical optimization loops also we can use. Then applications in chemistry, finance, and logistics, growing importance in near-term devices. So then applications in real world factors, where we have defined. Is it audible, all of you? I think I'm trying to convey the theoretical level only. Why means we don't have any AI tools can use to do for explaining the concept. That's why that algorithms also I keep into the notes to define the steps only. Okay, it's sorry for the inconveniences to handle these issues. Then we will follows to this. Sorry. Yeah. And then cryptography shows threatens RSA and AEC, optimization, groovers for NP hot problems, quantum chemistry, molecular simulation, drug discovery. So AIML as well via what kind of applications means quantum classifiers, quantum neural networks can use from that. Why AIML means we all of you know this, how the backend ChatGPT and Perplexity, how it will be function and how it will be trained to get into the content. All of you know this is the factors AIML applications using quantum neural network as well as quantum classifier as backend to work on it. That's why that fastest data has to generated and picking to the process. Google Quantum Supermassive is a milestone of practical demonstration of this process. Okay, then challenges and research directions. All of you know this: decoherence and noise, fragile qubit states, error corrections, resource intensive but essential. As scalability level, hardware limited to few hundred qubits. Then these are the challenges we are facing now. Then research frontiers, fault tolerant quantum computing, quantum error correction codes, post quantum cryptography. So these are the challenges as well as research directions as focusing into the applications. Then we conclude to these slides. Quantum state algorithm drive the quantum advantage. Key examples as Groover's shows and QB, VQE. These algorithms, what are the steps as used to do for made up of this quantum algorithm? We already have to seen into this. Then applications span across security, optimization, chemistry, AI, where we are approaching. What are the field as used from these applications? that chemical reaction, chemical molecules, and drug discovery we are using from these applications. Despite challenges, research momentum is strong. Then, quantum computing has a future of computational paradigm. This is a conclusion about this. Today, our entire quantum state algorithm objective of this answer, objective of this talk. Let us look into this. Any queries we will discuss on now.
Oh, thank you, sir. So I think so. There is no queries. So we'll conclude this section. Thank you, sir. Thank you, Naveen, sir. So I thank you very much for your delivering such an insightful and engagement section of Grover's and algorithm on other quantum algorithm. Your expertise and clear explanation of a complex concept, not only depth of understanding the quantum computing, but also inspiring our participants to explore this fascinating domain further. Thank you so much, sir.
Thank you, sir. The participants are requested to fill your feedback attendance link. It was posted in chat window. The date to attendance was posted in chat window. The participants are requested to fill the form. Amin sir, thank you so much, sir. Question side la irukku. How classical data is encoded in quantum data? Phone odinga.
Adinarayan sir, sir நீங்கள் ஏன்னா நீங்கள் இல்லை நீங்கள் பேசுகிறது எதுவுமே எனக்கு ஆடியோ வரணும், ஆடியோ மட்டும் ரீச் ஆகல சார். Oh, sure, sir, sure. Oh, okay, sir, okay, sir. Okay, sir, thank you. I think my audio is reaching you, but your voice, your side voice is not audible to me. Here some system issues or I don't know. So if you need any queries, please put on to that mail. Please type it here. Any queries, I will clarify you.
The participants are requested to send your queries through this mail ID
Thank you. Your voice is not audible to me.
Participants are requested to send your queries through this mail ID. You might have answered through a mail. Also, we request the participants to fill your feedback form, which was posted in that window, chat window. Once again, I thank you all. The participants may leave that Zoom meeting once you filled your application and then attendance form. Thank you. Thank you, Naveen sir. தெரியல. Completing all the 5-day session, the video might be posted through all the registered mail IDs, madam. Venkata S.P. Kumar sir. The recorded video send you once the completion of the FDP program. Thank you.
Excuse me. Once again, thank you all to listening my session. Thank you. I leave now. Thank you, ma'am.
Thank you, sir.
Recording.